Welcome to this design lecture. My name is Mark Scythian. The date today is August 7th, 2025. So here we have a DC series parallel electrical circuit which has been designed to power the DC electrical motor. So this is a continuation of a few previous presentations and lectures using the same electrical circuit design. So in this particular electrodynamics design application, we are going to power the motor across a drive line, a gear reduction unit, then connected to a pulley, which then functions as a weight hoist or a lift device. A 700-pound weight is lifted 30 feet. So a good set of design questions to ask is, how long will it take for the 700-pound weight to elevate 30 feet above ground level at low, medium, and high settings here on this parallel potentiometer circuit as a speed controller to the motor? And then the second question is, what is the DC electric motor's load RPM and foot-pounds torque at low, medium, and high settings? So we can start by accessing the low current setting output to the motor, 215.9 amps. So we would simply, in a DC circuit, multiply the current times the voltage, and to then determine the DC electrical power going into the motor, which is then multiplied times the efficiency of the motor, 72% electromotive efficiency, 0.72, to then calculate the mechanical power output at the motor's output drive to the drive gear. The gear assembly, or the gear train, has a 10% friction loss, so we would then take our 1865.4 watts mechanical power output of the motor and multiply this times 0.9 to then yield an effective mechanical power drive affecting the hoist and weight elevation. So that's 1678.8 watts mechanical, including the friction losses. From that point on, we can divide this into the number of watts to 1 horsepower. So there's 2.25 horsepower for the effective hoist power, and then simply convert this value to its foot-pounds per second mechanical power rating. So 550 foot-pounds per second equals 1 horsepower. So we calculate 1237.5 foot-pounds per second as the effective hoist power at low setting. So the next step is to define what mechanical power is in this case. So that is force times distance, in this case foot-pounds, over time, seconds. So we can solve for time algebraically. So then we can just place the low power effective hoist setting at the denominator, and then replace the force with the tension the hoist unit rope or line applies to lift the 700-pound mass. So this becomes a force tension of 700 pounds lbf times 30 feet distance. So then we have a calculation of 17 seconds, the time it takes the hoist to lift the weight at its low setting. So we can then continue the same method of calculation to solve for the medium setting. And so we calculate 8.5 seconds to lift the weight or the object, the 700-pound object at medium setting. And then we have our high setting, that's 647.6 amps current. So then we have an effective hoist power of 6.75 horsepower, so that's 3712.5 foot-pounds per second. And when solving into the power formula for time, we get 5.7 seconds also for the high setting. Next, we focus on the gear diameter. So the drive gear, the small gear, is 3 inches in diameter, and the output hoist gear, the large gear, is 3 feet in diameter, so 36 inches divided by 12. So we know the equation for calculating circumference is pi times d, d for diameter. So if we calculate the approximate diameter of the large gear, the approximate circumference of the large gear, I meant to say, we calculate 9.42 feet is the circumference of the large gear, the hoist lift gear here, the large gear. So we'll call that circumference 9.42 feet. And then we have the small gear, which has a diameter of 0.25 feet, which is 3 inches divided into 12 for 0.25 feet. We can simply just multiply 0.25 times pi, so we get 0.785 feet is the circumference of the drive gear. But we must also include the actual diameter of the pulley inner diameter for which the belt or the rope is connected upon, wrapped around. So it's approximately 2.5 inches in diameter, inner pulley diameter. So we convert that value into the feet diameter, 0.208 feet times pi, so we get an approximate circumference of the pulley drive circumference as 0.65 feet per every revolution. So if we were to take the number of turns the pulley has to make independent of calculating the gears, even though the pulley's rotation is connected to the large gear's rotation, but we'll focus just on the amount of turns this pulley has to make to then displace a height of 30 feet. So we can simply divide the 30 feet into 0.65. That would require 46.15 revolutions of the pulley to lift the 700-pound object 30 feet. So this allows us to then calculate the gear ratio. So we would simply just divide the circumference of the large gear into the small gear. So we have a 12-to-1 gear reduction ratio. So that will require 12 rotations of the small drive gear to get 1 rotation of the large hoist gear. So that means if we multiply 46.15 times 12, it would take the output drive gear 554 turns in order to lift the object, the 700-pound object, 30 feet. So we know now as a constant it's 554 revolutions of the small gear, which is the motor drive gear. So we have a 30-foot lift altitude, and we divide the 554 revolutions into 17 seconds for the low setting. So that's 32.6 revolutions per second times 60 seconds. That equates to 1956 RPM. So we just repeat the process for the medium and the high load RPM calculations. Now next we can calculate the foot-pounds torque, the load torque, the foot-pounds load torque at low, medium, and high settings. So we have to first access the brake horsepower formula for engines and motors. So this is any drive line powered by an engine or motor. Its brake horsepower, its usable power, so that is 2 pi, the number of radians to 1 revolution, times the RPM, times the foot-pounds torque divided into 33,000, which is the number of foot-pounds per minute to 1 horsepower. 550 times 60 is 33,000. So we start with a low setting again. So this time we can just calculate the mechanical power output of the motor, excluding the 10% friction loss of the gear train. So we're not interested in the gear train, only the mechanical power output of the motor, which is the 215.9 amps times 12 volts DC times the DC electric motor's efficiency of 72%, 0.72, so 1865.4 watts. We divide that into 746. This yields 2.5 brake horsepower output of the motor at the low setting. So now we can just substitute the RPM at the low setting load RPM into the equation, and then we can just simply algebraically solve for the torque. So we get 6.7 foot-pounds of torque is the low setting, low torque. So we carry on and solve the last two parts of the last inquiry in the same method. So again, it's a stable torque at 6.7 foot-pounds at medium setting, or at 3911 RPM. And so lastly, we have the high setting. We go up to the top right and substitute once again. So we calculate 7.5 brake horsepower at high setting. Is the DC electric motor's mechanical power output. So we calculate a slightly higher load torque at high setting of 6.75 foot-pounds. So now we'll officially enter the values. Thank you for watching this design lecture focusing on the electrodynamics application of a lift hoist.